Welcome, everyone. I'm going to be talking about a presentation that I actually put together quite a while ago, like 10 years ago almost, on Git Made Simple, because I've been using Git since its very, very early days. In fact, I know I was using it in earnest back in 2008. So this is something that I've given to a number of user groups and development teams and the rest to help them understand exactly how Git works. And that's been one of the big things that I've seen in my career is just how incredibly fast from essentially 2008 was about when it started to come out on the scene. I was definitely an early adopter on it. And then by about 2012, it had almost taken over the entire development community. And now at this point, I keep talking to senior developers that have never used anything but Git, which just blows my mind. But we'll be talking about Git and how it both how it does its magic, because there is a lot of magic that goes on inside Git, but it's not magic at all once you understand what's going on. And with that is, also kind of why it took over the world of software control management, revision control management, however you want to do that acronym. I sent out a link to these slides. There is going to be a ton of content, a lot of hashes, a lot of just code and the rest. Do not expect, even if you've been using Git since 2012 or 2008, to actually follow along everything that's going on, because there's just way too much content, a lot of details, etc. That's why you have this recording and those slides. So let's go ahead and get started. This is all the different things that I'll be covering. One of the big things that you won't see in here is pushes and pulls, fetch, workflow management, any of that kind of stuff. I'll be talking about just Git itself, not the workflows and the rest that it enables, though of course there will be a little bit of that. A little bit of a side note, as I noted earlier, I did this a long time ago. I have 3 daughters, and the oldest 2 were in preschool at the time. I was surrounded by a lot of My Little Pony. Hopefully everybody knows this guy. This is Linus Torvalds. He is the creator of Linux. He is also the creator of Git. He named Git after himself, as he famously says, Git being a rather nasty British term for a nasty person or stupid person, those kinds of things. But he created it very much with that Linux philosophy in mind, that Unix philosophy in mind, and knowing all the things that he does about how low-level operations work and operating systems work and the rest. We'll see an awful lot of that. A lot of how Git works is very, very blatantly following that Unix philosophy. So along those lines, let's go ahead and create a repo. I'll be using Unix commands here. If you're not a Unix person, don't worry, I'll kind of talk through pieces of this that Windows person may or may not understand, but a whole lot of command line operations, just because, again, we're going to be taking a look at data structures. We're going to be taking a look at what it actually stores in the file system. We're going to be taking a look at the innards of how Git works. So I'm going to make a directory, git temp, go into that directory, git init, configure my username and email, all things that every Git user is used to. And now at this point, I'm just going to create a few files, 3 files specifically. The first one with some cowbell in it, another one with some file2 data, and then I'm going to create a subdirectory and copy the first file into file 3. So as it says there, we now have 2 identical files in 2 different places on the file system and another different file. So that is where we start getting into some of the things that make Git very different than other file control systems that you might be aware of. So how do we identify that content? Um, so we want to keep track of the content and know when that content has changed, because for revision control, of course, that's the most important thing. And ideally in a way that the name and identifier would survive context shifts. Classic examples of where that turns out to be a problem if you're not following these techniques that we'll be talking about in a moment is, like you have a Word file that you mail around to people. Hey, comment on this. And, what's typical in Word files is you'll have like a revision control block in the front of it where people keep track of versions and, hey, this is the change that was made, etc. But if multiple people are making changes on it and it was emailed around, and if some people are storing it on their Macs and some people are on their Windows and they're storing it in different places, and they might rename it because they make version 1-2 and another person says 1-me, and all those kinds of things where the content may still be identical, but it's going on to different people's machines, different people's operating systems, different people's naming schemes, et cetera, et cetera. And when you're trying to track things like source code, you don't really care too much necessarily about the name of the file, though we will see that we do. But what's really important is the content of that file. So the file name obviously is out because people can rename things. Using like a universal resource name and modification time, maybe, kind of. If you're familiar with classic version control systems before Git, like Subversion or CVS or RCS or VSS or Perforce or, pretty much everything other than Git or Mercurial, those all use revision numbers. And it's typically a monotomically increasing version number. And in order to make that work from a monatomic standpoint, you have to have it at the server that's keeping track of everything. And so what you would often have to do for those systems is you would have to check out the file and then have a lock on that file so that when you upload that file, the server would be able to handle the revision control on that. Newer systems like SVN or even CVS allowed you to do that without necessarily checking out that file, again, putting a lock on that file, but they had their own issues. SVN, one of the big things with it is it was much better at that than previous things, which thankfully, since it became very quickly the de facto standard with the rise of the internet becoming very, very big, worked out very well. But we found out as open source really started to get going and as things really needed to scale for the age of the internet, that having a centralized server and having those kinds of controls on things just did not scale. And so none of these work. So moving on, especially think about the kinds of problems that Linus had to solve for working with, the Linux operating system. Very famously, many thousands of developers contributing to Linux, and some of them in, countries and locations where, you're dealing with the best you can hope for is SMTP, email, or Usenet back in the day, for transferring these things around, a lot of UDP, a lot of things where it's just impossible to keep track of things in any kind of always connected kind of situation. Or again, where people have different operating systems and different types of file systems across all these different domains. And so that was the problem that he was solving for in creating Git. So what we're going to do is, like I said, base things on the content rather than these things that are effectively random because of all those different situations. The way that you do that, hopefully every computer science person knows, is with a hash function. So that's any function that can be used to map data of arbitrary size to data of a fixed size. In the case of Git, the particular kind of hash function is what's known as a SHA-1. And with that, it's also a cryptographic hash. We'll talk about some of the characteristics of that. But again, what a hash function means is that if you've got something that you're hashing that's 1 bit or 300 terabytes, the end result value for that hash function, the value that comes out, is always of the same size. So like I said, in the particular case of Git, it's using the SHA-1 algorithm, which is 160 bits. And so if you do, in this particular case, we're going to go git hash object file1.txt. There is what that hashes out to. If you run this on your computer, you will notice that it will come to exactly that value. And all this git hash object is if you do like a cat or a type and pipe it into the SHA-1 algorithm, which many operating systems have just as part of their bin, or you could pass it into like Ruby-E or Python or whatever, anything that'll run a stream through the SHA-1 algorithm, they'll all do exactly the same thing. So all that git hash object is basically doing is it's piping the contents of that file through the SHA-1 algorithm. It always gives results of exactly the same length. There's file 2, something completely different. And if we run it on file 3, because it had exactly the same content, because we did the copy over, of file 1, notice it has exactly the same hash. At this point, it's worth bringing up that Git has the concept of porcelain versus plumbing. And just like in your bathroom, you typically interact with the sink, the porcelain, that larger entity that brings together all the various plumbing pieces. But obviously, it's the plumbing that makes it work. In Git, you have much the same concept. You have a lot of commands, a lot of programs, going with the Unix philosophy of doing things, do one thing, do it well, that are plumbing. And then there are the porcelain commands. We'll take a look at more of those that are what you tend to actually interact with. This git hash object is an example of a plumbing command. In normal use, you would never see that. For normal use, you deal with things like git checkout, git commit, git add. Those are all porcelain commands. And as we'll see later, they actually are a stringing together of those plumbing commands that we'll take a look at a few of them. Because again, since we're taking a look at how Git actually works, we're going to take a look at the plumbing. All right, so we're going to identify what we want to save to the repository. So we're going to go git add file 1, file 2, file 3, and that's basically queuing things up to go into the repository. And now we go git ls files. Ls is the Unix command for listing on the file system. So this is essentially, okay, Git, show me the files that you know about. And the -- stage is because we want to know about the things that are in the staging area of Git. It's also known as the index and the like. We'll talk more about that later. But so we're basically telling Git, hey, I want to now track these files. Nothing's in the repository yet. It's just in the staging area. But this is showing us information. A few things to notice in this is over on the left-hand side, you see what is the Unix bitmap for change mod, if you're familiar with Unix. Here's the hash value that it comes out to, and this is the file name relative to the top of Git. Now we're going to actually put it into the repository. And with that, we're going to go git commit, and we're going to give it a message, first good version. And it lists, okay, we are on the master branch. This is the root commit, so it has no parent. That is the hash for the commit. We'll talk more about that in a moment. There's the message that we did. It says, okay, you have 3 files involving 3 insertions. There you go. The ID for this is, we're only listing 7 characters here because that's enough to make it unique, almost guaranteed regardless of the repository. But what's actually being stored, of course, is the 160 bits. If we want to actually take a look at that commit, what we can do is another plumbing command, git cat file. Cat is a Unix command for looking into a file, and so there we go. All this is doing, you can do this yourself, is if you catted the file, I'll show you exactly where the file is stored in the file system. Excuse me. If you cat the file pointed at by that hash key, this is what it would show you. That's a slight, not entirely true. We'll talk about that in a moment. But what it really is if then you pass it through zlib, because what it's storing on the file system are zlibbed things, but this is following Unix. And Unix, as opposed to like Windows that stores things into the registry and binary format and the rest, Unix, if you're a Unix person, it stores everything. All your control files and everything are in plain text on files. And Linus, being a Unix guy, did exactly that. All of these files, everything that's storing on the file system is just plain text, especially for its metadata. And this is exactly what the commit looks like. So the different fields that you can see in here, tree, author, committer, these are the different fields that are involved with that. You can have 0 to n parents. We'll see a little bit of that later. In this case, we have 0 because it's the root, but we'll see more parents later. If we want to take a look at the trees, the file system effectively, it's not actually the file system, but kind of Git's version of the file system. We can take a look at, okay, so what are we looking at? From here, it says my tree is this big long hash. So if we take the first 7 characters of that big long hash, let's take a look at it, and boom, this is what we saw before when we did that git ls command. The only difference here is now we can see, okay, the type of this file is a blob, and a tree. Notice there's no file3 over here because this is a tree. This is, if we follow this, this is the contents of that tree. And so you have the concept of subtrees going down through the tree. If we actually take a look at 77BD771, which is file 3 here and file 1 here, you can see some cowbell. Now on the file system, if you were following up to this point, this is exactly what you would see on your file system. Again, small caveat, we'll talk about that in a moment. Find.get objects type F, which means basically show me all the files under that file structure. And there we go. Here's our tree. You should notice that this is that same hash, the commit that we were looking at. Here's file 1 and file 3. What it's doing here is it's breaking it off, taking the first 2 characters of the hash and breaking that off into subdirectories, because file systems don't like to have hundreds of thousands of files in the same directory. So this is just doing a namespace thing to help distribute that. But as we'll see, Git actually helps prevent that from being too much of a problem. But this is making sure that it never is a problem. Because if you've ever worked with large FTP systems or anything like that, where people are trying to shove hundreds of thousands of files into a single directory, file systems generally do not like that. So there's our file system structure. If we take a look at cat git head, we see that it's a reference to refs heads master. If we take a look at refs heads master, it's referring to this hash, which is this commit, And we already saw what that commit looks like. It points to this tree, and this tree points to these files. So this is what it looks like if we use GraphViz on that to map that out. We've got our head that points to master. Master points to this SHA for the commit. That commit points to the tree, and the tree points to the blobs and the subtree. Now it is time for more cowbell. We're going to put more cowbell into file 1, and we're going to do a new commit that says that we added more cowbell. And with this, this is saying this is the SHA that we just created. If we take a look inside it, you notice there's a new field in there called parent that points to the parent of this commit, and you can follow through the rest of that if you wish. So what that looks like now is that commit has a pointer to its parent. There is a new tree object that is created, and it's pointing off to exactly the same things. Notice though that even though there's a new tree object, there's no new blobs. There's one new blob because we changed what I was looking at for file 1. Notice that file 3 did not change, so the tree object still points to the blob for file 3. That still exists. Nothing changed for that. Renaming the files. I will just point out that you have the slides, so you can go back through this at your leisure because it's going to get even more complicated. We're going to rename some files. So we're going to rename file 2 to while.txt, rename the subdirectory from more files to has files, and we're going to create a new commit that does nothing but say, hey, I renamed these files. And notice it says here, 2 files changed, no insertions, no deletions, and it noticed that I renamed this file and I renamed this file. We did not say rename this file. If you are familiar with older version control systems like Subversion, I'm going to refer back to Subversion because that was the de facto before Git, but same kind of thing that you had to do for like Perforce and VSS and those kinds of systems. Sadly, I was admins for all of those. I've had to deal with the innards of all of those. But if you've worked with like Subversion or Perforce or any of the rest, you would have to say like svn mv, move this file to this file in order to alert it, hey, I'm renaming this file. You don't have to do that with Git. And we'll talk about why. Hopefully by now you've figured it out, but we'll talk about why. If we take a look at the commit itself, we could again see much of the same information that we saw before. There's our tree. And again, we still have exactly 3 blobs. Our subtree hasn't changed at all, even though this tree has changed because it has this new piece of information in it and this new piece of information in it. Because this content changed, that means that it generated a new hash for that for those values that are inside there. Because this is different content. So if you SHA this content, it's going to be a new value. So same thing for the tree. That SHAs out to be this. This SHAs out to be that. And so all of those are guaranteeing that as we make changes at the appropriate places, it automatically gets propagated up through the system. Now, what's really nice, as we were just talking about, is that a change in one of those sub-objects guarantees that a parent object will also be different. Because that tree down here was different, that's why this commit has to also be different, because it hashes out to a different value. Okay, so what's going on here is that data structure that we're talking about is what's known as, in formal terms, a Merkle tree. More conventionally, it's known as a hash tree. If you're familiar with, especially if you did C or any of that kind of stuff where you're dealing a lot with pointers, you create trees all the time with pointers, or in more modern languages, it's with references, but same basic idea. Here, instead of using memory addresses for our pointers, we're using hash addresses, where we're hashing the content and we're creating the tree based on those hashes that identify the contents. Just like a memory address normally identifies the contents in memory, these hashes are identifying the contents of these blobs. One thing that's really nice about this is, if you're familiar with this technique, this is what's used for distributed computing. Everything from ZFS, React, Cassandra, BitTorrent, Bitcoin, they all use this technique. When you talk about things like the blockchain for Bitcoin, that's effectively what this is. It's only, instead of a tree that goes out, it's more of a list, a linked list, but it's exactly the same idea. Everything is based off of these hashes, because it does not matter where that hash is generated. It's pure math. And so if you're generating it on an Amiga, or you're generating it on some Raspberry Pi supercomputer, it does not matter. You are always going to get the same value out of that math function. So that's why it is used everywhere for distributed computing. And we're just talking about the fact that it is in fact a graph as opposed to a linked list in the case of the blockchain. So we have a DAG, directed acyclic graph. Again, it's based on these hashes, and because those hashes are guaranteed to be the same regardless of where they are generated, you have full consistency. One thing I didn't mention before was because SHA-1 is in fact a cryptographic hash, that means that if you are creating the hash of the ASCII letter A, and it will give you one hash. If you're creating a hash of the ASCII character B, it will give you a completely different hash that looks completely different. There's no way to backwards go back and figure out that this big 160-bit value is representing something that was 1 bit different than this other value. And that's one of the reasons why you are able to have guarantees around the integrity of your system, because there's no way to go back the other direction. If you're familiar with how hacking works on a lot of these systems where you do in fact try to crack some of these keys, there are ways around that, but it's really, really hard. And one thing to remember is that when Linus was designing this, he had two things that he had to keep in balance, and the reason why he chose SHA-1 in designing it. One is that he had to use a value that was going to be reasonably computational on systems from 2005, which is when he originally wrote Git, on all the different systems for all the different contributors around the world. He had to use something that would be reasonable for all those systems to compute. The other thing that he had to work out was he needed to have that cryptographic certainty, because think about what Linux runs on, or more accurately, what runs on Linux. If the integrity of Linux is ever in doubt, that breaks the internet. That breaks all of computing, civilization. And so he had to make sure that it was going to be something that was guaranteed to be correct. Could not get it, you have to know that if you receive something from, kernel.org, and you have a particular hash code associated with a revision, that it is correct, period. There's a few other techniques that he uses to help ensure that, but those are the competing forces that he used. in picking that particular algorithm. Now, back to here, because identical content hashes all compute to the same value, and you have all of the content all the time, we'll talk about that in a moment, it's trivial to do the consistency checks needed to know exactly where, when, and how content diverged, even among systems that have no communication between them. Again, this is a basis of modern distributed systems. So there's no need to know how you're going to want to slice and dice that information ahead of time, like in the case of our rename. We'll see a couple of other examples. So one of the things that it does is that porcelain that we used, like commit, did the rename detection. If you're familiar with how it does that, there's different ways that you can actually, because again, it's not actually a rename as far as Git is concerned. It's just a new blob with a different tree value. But it's able to do a nice simple computation on it to detect that it was a rename. But there's different controls that you can do in order to say, okay, it's a rename or a copy if it's 70% the same. If you think in terms of like Java, for example, if you move a class from one package to another, you're going to have like one line in that file that changed, but just that one line. And Git will notice, oh, okay, well, this is close enough, so I'm going to assume that it's just a rename. A few of those kinds of things. And in fact, if you really want to get fancy, you can do like git blame-m, and it will notice that like, okay, I copied this function from this file to this file. And it's able to detect that because again, it has the full provenance of the contents of those files at all time. So it's just a computation that it needs to do, a comparison computation. Now, one thing that really makes Git stand out from prior revision control systems is that it's not storing deltas, it's not storing patches. If you're familiar with any of those prior ones, that's exactly what they did because it seemed to make sense. If I want to, especially for older revision control systems before we had terabytes of data on all of our laptops and the rest, you wanted to be a bbit more conservative on your space use. And so what they did, instead of like, okay, I've got this 200K file and I change a line of that 200K file, which is the kind of thing that you often do when you're doing software development. You change a line or a small handful of lines. So hopefully it's not 200K, but what you want to then store, it would seem is obvious, is just the fact that there's the patch, just this change. And so you put into your revision control system, oh, I just made this change. And the next time you make a change, oh, just this change. And which would seem to make sense when you're talking about, again, especially source code, where you're changing little bits and pieces of lots of files rather than, like completely changing out things all the time. But that's not how Git operates. It's not working on patches or deltas. It is storing the complete blob every single time. One nice feature of that is that that means that moving from version to version is an O1 operation for all you computer science people out there. It's a constant time operation. You're just moving a pointer. So if you're moving from first revision to the 5,000th revision, it's an O1 operation, extremely fast. If you want to compare the first version to the 5,000th version, you're just comparing pointers. As opposed to if you do it the delta approach, the patch approach, you have to reapply every one of those patches 5,000 times to go from 0 to 5,000. And considering that, especially if you want to compare, okay, this thing that I did a quarter ago, so 3 months ago, versus my revision now, because I've got quarterly releases or whatever, which would be stupid, but guess what? We as an industry do that kind of thing. But if I want to compare 3 months worth of changes, that means that I have to apply 3 months worth of deltas. With this, no such thing. It's, pointer to pointer, O1 operation. Now, what you might think would be the case is that, oh my goodness, if I've got these, again, let's just assume they're 200K files for these source code files, then it's going to just blow out your disk requirements. Thing is no, it does not. Again, going back to Subversion, just because that's the one that most people are familiar with, that they're it was the de facto standard before Git, is if you remember Subversion, it would store on your machine .svn directories under every one of your directories. And it would have under those .svn directories a copy of the file according to its latest revision in the repository. That way, it meant that you could do a diff of, here's my local changes in my working directory, and diff it against what's in the repository. That was a caching mechanism that Subversion used, as well as knowing like what files actually changed for sending up to the repository. Now, as many of you know, back in 2008, I was working for SpringSource. And if you're familiar with SpringSource, they're the creators of the Spring framework. Now more popularly known for Spring Boot, but the Spring framework is not a small project. Many, many thousands of files, many, many, many thousands of revisions involved in that project. It's extremely large, very, very popular, but extremely large project, especially for an open source project. Not quite Linux, but very, very large project. And I was working with SpringSource. I was also traveling. I was consulting and training. I was constantly on the plane in order to do all of that, going over the latest changes that were going on in the framework. So I had all of it on my laptop. I'd go on a plane, and of course, from the plane, I couldn't really do much of anything because I'm not connected, especially not in 2008. And so Git came along, and they had a SVN to Git converter and back and forth. And so you could actually work locally in Git and still translate it back and forth to your SVN server, which is what pretty much everybody was using at the time, including SpringSource. So I was like, hey, this is really awesome because I could put it on my laptop. I can be on the plane. I can be in a hotel with a crappy hotel internet connections and still be able to do my work and compare things and do all that kind of stuff. But it's like, wow, it's storing the entire repository on my machine. Just how huge is that? So I did an experiment. I let it had the ability to let you do a conversion operation to go from Subversion and convert the Subversion repository into a Git repository with all the revisions. So I'm like, okay, I'm going to do that. So I ran it. It took, I think it was about 16 hours to do that because it's check out this, the first revision, check out the second revision, one revision at a time, just walked through everything. And as I said, it was not a small project. It took about 16 hours to convert the entire Subversion repository into Git. And so now under my .git directory for the Spring framework, I now had the entire history of the project on my laptop. The next thing I did, I don't still have the numbers. I really, really wish I still had the numbers. But the very next thing that I did was I checked, okay, what's the size on disk of my .git directory? And then what's the size on disk of all my various .svn directories that were scattered throughout the file system? It was smaller under .git than under all the .svns. Now, that doesn't make any sense. I have every revision of everything, and it's storing the complete file every single time. except it makes perfect sense if you think about the kind of content that you're working with. And like it says on this slide, zlib compress it. So what it was doing is, remember before where we're making all those changes, but it wasn't actually creating new blobs unless there was in fact a new blob. When you're working with source code for all those different revisions, even though there's thousands of files, you probably only changed a couple. For each one of those commits, only a few new blobs. And then for the source code, zlib compressing that works really, really well. It's text, and the vast majority of it is exactly the same. Especially when you're dealing with Java, because Java is very highly ceremonial, and so a lot of it looked exactly the same. Zlib can compress the heck out of that. So between that and a lot of the other assumptions that you're able to make, because this is all immutable, that meant, especially if you're familiar with like persistent collections and that kind of stuff, it makes perfect sense that the entire repository for all revisions throughout time for this large repository would be smaller, storing those individual blobs, the full file, rather than the patches. But it was not obvious at the time. But apparently it was to Linus, and yay on him. He's a smart guy. So, as we saw when we took a look at the git directory, especially under objects, which is where it's actually storing those commit files, the tree files, the blob files. It's storing individual files for every one of those objects. The thing is, though, is, especially if you've ever worked in databases, you should really know this, is if you have a highly transactional system where you're doing lots and lots and lots of writes, what you want is lots of small writes. You want a highly normalized database when you're doing lots of writes. It saves a lot on the amount of space that you use. But even more importantly, it saves a lot on the amount of time involved in it, because you're writing out small little pieces of information. If, on the other hand, you're writing lots of reports, you've got your OLAP systems and all those kinds of things, you do not want a highly normalized database. You want a highly denormalized database, where instead of lots of little tables that are joined, you want, ideally, one flat table that you're working with, which is one of the reasons why some of these NoSQL systems, like the Mongos and Cassandras and the rest, tend to do very wide things, or your documents and the rest. You lose a lot when you do that, but you gain other things. And so it's one of the main things these days for choosing a persistence mechanism. Relational databases are really, really good at being normalized, and a lot of those other systems are really, really good at being denormalized. And so you choose the appropriate technology for your use case. If you're also familiar with a lot of the modern patterns, there's the pattern CQRS, which is all about, hey, you use one pattern and potentially one system for your writes, and potentially an entirely different database and persistence mechanism, but certainly different services for your reads, because you have different requirements around that. So why did I talk about all that for Git? Well, when you're doing your commits, when you're doing a lot of your day-to-day stuff for that, what you're doing is you're doing a lot of writing. And so it's going to write it out to those individual little files. However, you are also going to want to do some reads. And so every once in a while, it will automatically, you may or may not have noticed this before, but it'll automatically do a GC, a garbage collection. And as part of doing that GC, it will also do a pack. And what happens here, I'm manually running the GC. And notice this is the same command that I ran before, but it's not picking up those individual blobs and trees and commit objects. It's picking up a pack with an index and the actual data. And so that's a highly denormalized structure now, a very flat structure, so extremely efficient to read. The nice thing about this is you don't have to lock that file or anything because it's immutable. And so again, one of those really nice conditions where, since we know it's immutable, we don't have to lock it, we don't have to do any of that kind of stuff. We can make these kinds of optimizing decisions to give us both extremely fast writes as well as extremely fast reads. And we already talked about it in terms of like both the reads and the writes, because we're doing O1, because we're storing full objects, keeps things really easy. Now the index. This is what is most awesome about Git. A lot of the stuff that we just talked about is really cool. But from a day-to-day usage, this is what's awesome. And it's the part that almost nobody understands, is the index. Especially if you're a poor sap like me that's been doing this for far too long and you've worked with the prior revision control systems. I remember going from Subversion to Git. This was the part that just really I did not understand until I had been using it for a long time. It's like, why in the world? Because on Subversion you would do like subversion commit, here's the file, and it would just commit the file. But with Git, you have to have that add operation in between. You can do the git commit -a and it'll do it kind of for you automatically, but it's still doing that add operation. It never really made sense why it had to do that add operation, where every other version control system I had ever used did not require it. But what if I want to be able to add some files, but not all of them to a specific commit? You could do that in the other ones, but we're going to see some other stuff. I want to be able to add some parts of a file to a commit, but not others. So one thing I tend to do a lot is, like I'll make a whole bunch of changes as part of something, as part of like a big refactor or something. But personally, I view commits as communication, whether that's to me or somebody else, but I view commits as communication. I want to see, again, the provenance of a file on how things changed. And if I made multiple different kinds of changes within the same file, I want to be able to break that up into multiple commits to, again, kind of give that story on how things actually change. So what I used to have to do in order to do that was I would have my source code open in one window, and I would have like Notepad open in another window, and I would copy the source code from it. And I would restore things back, and then I'd copy over, okay, here's my changes that I want to actually check in. I do the check-in. I bring over the other changes I want to check in. I check those in, but very kind of manual process. You don't have to do that with Git. I'll show you an example of that later. But so you can do just like, okay, these are the changes. These are the lines that I actually want to be a part of this commit. Everything else, just ignore, and I'll take care of those later. I want to be able to move the commit pointer without affecting the files in the working directory. Classic examples of this are, oops, I didn't mean to commit the password file. Or I had a typo in the commit message. So I want to move things back and just redo the commit message. Or any other kind of oops. Improving the readability, understandability of the project's history. Again, I see the project's history as being part of its documentation, and especially technical documentation. And so I like to have a very clear history. And so sometimes I'll move things around in order to make that clearer. And the primary reason why I can never use a system other than Git again is a desire to project the illusion of undeserved competence. Because this is really, really awesome once you understand it. I can go make a whole lot of changes, follow a whole lot of rabbit trails, and as we'll talk about later, I'm a TDD guy. I do test-driven development, test-driven design, and so I'll write some code and write the test, or I'll write the test and I'll write some code, either way. But every time I see green, in other words, every time that the tests pass, I commit. I make another change, test pass, commit. Make another change, test pass, commit. Boom, 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 boom. So especially when I'm on a roll, if I'm in the flow, then I'm making changes every couple minutes. And especially for something significant, that can mean easily dozens of commits that are going on. If I did that with Subversion or most other systems, that would create a huge amount of noise in the commit history. But it doesn't for Git. I could be making all those changes, and so I have the ability to roll back if I make some sort of mistake, if I follow the wrong rabbit trail. And with that, I've got the full power of my version control system behind me. So I have the full ability to be very fearless in how I'm moving forward and trying to solve a particular problem, because I always know that I can always move back to a previous version. I make all of those changes and I get things exactly the way that I want them to. I then squash them into, here is this nice pristine commit, and that's what I push up to the server. So what everybody else sees is not all those rabbit trails that I followed, making stupid mistakes and doing all those kinds of things. They see something that appears to have come out of the head of God, which is awesome. All right, so all problems in computer science can be solved by another level of indirection. David Wheeler, beautiful code. So that's what the index is for. So instead of just the working directory and the repository, there's also the index. It's also known as the dir cache, the staging area. It uses all of those terms in Git's documentation itself, which makes it really confusing. But so if you see dir cache, if you see staging, if you see index, they're all referring to exactly the same thing. The life cycle of how content moves on the system is from your working directory into the index, into the tree, into the commit. So if you remember back when, at the very, very beginning, when we did that initial add and we did the ls files, that was just putting things into staging, into the index. There is not a tree yet. There's not a tree object. And there is not anything in the repository. This is just in the staging area. This is just in the index after we do the add, which is one of the reasons why if you do like a git status and you see a file that you added and then you made some more changes to it, you notice that there's two different statuses associated with it. That's reflecting the fact that it's got one status according to what's in the working directory, and it's got a different status according to what's in the staging area. So there's our life cycle that we're moving from the working directory into the index, into the tree, into the commit. Because remember, the commit needs the tree to reference the blobs that were in the index, and yeah. So the different ways that we manipulate the index are with git add or git rm. You can do git add-p, which does that patch capability that we talked about just a little while ago. You can also do reset, which is the way that you actually basically do your pointer manipulation. So if we do git reset head ~1, that's saying I want to move the pointer, but I don't want you to actually change what's in my working directory. There's a git reset soft that allows you to change the working directory without moving your pointer. I've never seen a use case for that, but or the other one that people use all the time is git reset hard. If you don't specify head, it assumes head, but that's a very, very common one, basically going, hey, forget I did anything, I made a whole bunch of mistakes, just move me back to the last commit that I had. In source tree, here's an example of letting you stage these particular lines. So if I don't want to add these lines to the staging area or these lines to the staging area, I can just select these and stage just that change, and that's what actually gets put into the commit. For most things, I'm a command line guy. I'm sure you've probably noticed, but this is definitely one of those things where having a UI makes things a lot easier. References. Git tag. So I'm going to create a tag called a tag because I'm very creative in my naming. And if I take a look, if I do a regular cat on that file, notice that it's pointing to a hash. If I want to take a look at what type of thing is the hash pointing to, that's what the -t means, as opposed to the -p. -p is print the contents, -t is to give me the type. The type of thing that that's pointing to is a commit. And that's what people often use. That's what's known as a lightweight tag. And the only thing associated with that is this file. It creates that reference that has this file, that has that value in it. That's a lightweight tag. You can also have an annotated tag, also known as a heavyweight tag, but annotated is a better term for it. And what that does is it actually creates an object. The objects that we've seen so far that Git tracks are blobs, trees, and commits. This is a fourth kind of object, an annotated tag. It's essentially, as you can see down here, like a commit, but it's not a commit because you're usually pointing to a commit. But it has much the same information. So you can put a commit message, a tag message, a commit message as part of it. It keeps track of who did it and all those kinds of things. What's particularly nice about this, as opposed to a lightweight tag, is it's then actually a part of the repository itself. It's not just a text pointer. It's part of the repository. And so it gets tracked as such. It receives its own hash value. As you can see here, it receives its own hash value and everything. Also, because you could put anything you like in here, one of the more popular things to put in here is like release notes associated with that tag. So I have now tagged version 1.3.4 of my software and of my, and I can put the release notes for that version right there in the tag. So it's now part of the repository. The other thing that you can put in there is a digital signature, which is exactly what Linus does to sign the particular versions in his repository of the Linux source code. So again, if you check out a particular tag from the repository, you can double check against his public key credential that he signed that tag. And so you know that everything that tag points to, that he has validated it and he is putting his reputation behind it. So you can put digital signatures in there. You can put a lot of things in there. Anything that you can put into a blob of something, typically with a base 64, all those different kinds of things. So very, very useful extra piece of metadata that you can associate with your repository. Branches. We saw this sort of when we took a look at head earlier, but the big difference between branches and tags is that even for lightweight tags, it's expected. It's not guaranteed in any way, because a lightweight tag is just a file that has a value in it, but it's not hashed. With branches are also not hashed because it's just a reference, but it points to something. In this case, it's pointing to that same commit that we were talking about before. The primary difference between branches and tags is the way that they're used. Tags are expected to be stable. Branches are expected to not be, because of course, the commit that the master branch is pointing to is expected to change as you do development. So as we were just talking about, the contents of our objects can never change, and it's guaranteed because they get hashed. And so if you change one bit of it, literally one bit, it changes everything. And that propagates all the way on up through. And in fact, if you ever want to just verify everything, you can run a git fsck, which, again, if you're familiar with Unix, that's the file system check. And you can run the same thing on a Git repository, and it will verify that all the pointers line up, and it will tell you if any of those pointers are not correct. So references may change, which is why they don't have a hash. And head isn't technically a reference. Notice it's not under the refs directory. It's used as part of the porcelain. In fact, if like you take a look at the repository as it exists up on like a GitHub or GitLab, it doesn't have that same head. It's got a remote head, which keeps track of, essentially that server-side porcelain of what's going on to keep track of where the user is. Or in the case of remote repositories, where kind of the main branch is the integration branch that everybody's kind of working around. When you do certain operations, you'll sometimes see messages saying like, hey, you're working on a detached head, which sounds really violent. It's not. All it means is that instead of pointing to a branch, the head is pointing to a particular commit. So the head isn't going to be moving, implicitly as you're making changes. And so that means that if you're doing a workflow, like you're creating new commits that are assuming that the head is also going to be moving, then that's a wrong assumption, which is why it warns you, hey, you're working with a detached head. But that's all detached head means, is that the head is pointing to a particular commit as opposed to a branch, which then points to a particular commit. And as we'll see, there are very good reasons to have detached heads. But like with everything else, it's very useful to understand exactly what it is and why it's there. Revision IDs, at this point, hopefully, nobody's very surprised by what this is. But, so if you see a specific hash, whether it be the 7 characters or the 42 characters, or a ref name, like branch name, tag, head, etc. This is something that people use. I avoid it because they'll use like master caret in order to point to the parent of master. However, I always use the tilde with a number. The reason why is because like if I want to go to 5 commits back, which is common for things like rebases or diffs or those kinds of things, then you can do tilde and the number of revisions to go back. Nice and easy. If you use the tilde notation, you would have to go master tilde 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 to go back 5 revisions. So it's just easier to do the consistency with the caret 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 as opposed to head tilde 5. All right, so applying changes. We're going to, what happens, add is a porcelain command. What's the plumbing that goes on underneath the add? If you don't recognize this guy, as I said, back when I wrote this, I had preschoolers. And so they watched a lot of Disney Junior. There's a program on Disney Junior. It's not on anymore, but called Special Agent Oso. And he would teach preschoolers the 3 simple steps for like how to play a game or how to make a snack or, the kinds of things that preschoolers need to learn how to do. And they would always break it down into 3 simple steps, because that's what people can deal with, is including toddlers and preschoolers, is 3 simple steps. And guess what? Virtually all of these commands that I'm going to show you, they break down to 3 simple steps. So for add, it's compare the working directory hash of the file to what's in the index. If the hashes are different, copy the file into the object store as a new blob, and then record the hash for the file in the index. That's what add does. If we take a look at commit, it writes the index out as a tree object. It creates a commit object that has the tree's hash and metadata, as we saw at the very beginning, and then we update the head of the branch pointed to by head. Nice and simple. 3 simple steps. Get checkout. We replace the index with the tree for the commit. We update the local file system to match the index, if you remember the life cycle. And then we change the head to point to the branch. if we do a cherry pick, the process is simple. We do a diff from the previous revision to this revision to create a patch. We apply the patch to the current head, and then we create a new commit, copying over the metadata from the cherry-picked commit. 3 simple steps. That's what a cherry pick does. Notice that it always does exactly 1 revision change for that cherry pick, which is something that people often don't quite get when you actually start talking about cherry picks. It does exactly 1 revision change as a diff to create that patch. Merging and rebasing. So when we do a merge, which is what most legacy revision control systems would do, was they would work with merges, though they would do it slightly differently. But in Git, what merge means is a new commit object is created with 2 parents. More parents are possible, but don't do it. People will hurt you. In fact, if you see like the different merge types, there's the octopus merge because you can do n number of merges. If you saw the data structure that we referred to before, 4 commits, you could have n number of parents. Again, don't do it. You typically want either exactly 0, 1, or 2. Going beyond 2 is going to hurt people's brains when they try to figure out what's going on. You'll also break a lot of tools. Now for merging, technically we're doing 3 steps, but they're not as simple of steps. So the trees of both parents are examined, finding their common parent. Identical trees and blobs are added to the index. A consistency check is done for the common parent to detect if both have been added or removed files. Perform 3-way merges on changes, creating new blobs and adding their hashes to the index. And then you create a new tree from the index, and then you create a commit. So it's this first one that is definitely much more complicated than what we saw with a cherry pick. So what this looks like, to kind of graph it out, is if our current branch, if our head is pointing to branch 1, and so we're looking at commit 2 that has a parent of commit 1, in this kind of structure. And there's also a branch 2, that's pointing at a different commit, but also has the same parent of commit 1. When we run that command, what happens is a new commit 4, is created that has both of those as its parent. Branch 2 is still pointing to commit 3, but because of the various merges and stuff that happen, almost certainly a new tree would be created. Not necessarily, but 99% of the time. A new tree is created that points to many of the same files that were there before, but as a result of the 3-way merge that typically happens as part of doing a merge operation, you have new blobs that are created, and therefore the new tree, and therefore the new commit. So that's what happens when you do a git merge. What's beautiful is that since we're just dealing with pointers, that means that we can do a lot of the pointer trickery that we do in our programming languages when we're working with trees and working with pointers. So for example, if we do a -s, which means -s hours, that means use the hours strategy for doing merge. And what that does is essentially it will say, okay, I'm using commit 3 as my parent, as one of the parents for my new commit, but yeah, let's not actually look at anything that was under commit 3. Let's only use the data that was under commit 2. So it points directly from the new commit to the same tree that commit 2 was using. Now, why would you ever do something like that? Well, this is really awesome, because depending upon what your release process is for keeping track of things, say, for example, you've got your development branch and integration branch where everything's going on, but you also have a release branch that's staying relatively stable, especially if you're not doing full-on continuous delivery, continuous deployments. And so you might be releasing every month or every quarter. But so for that time period, you need to have a branch available, and you know what's going on there, or at least you can always create a branch off of that known last tag, that known last revision. So you have a release branch, and on there, you've got your people that are creating hot fixes against that release, hopefully then integrating them back on the development branch onto master, onto head, onto your integration branch, and bringing those back in. But that way you're able to create those hot fixes, put those onto the release branch, bring those hot fixes into your integration branch onto master, and just keep on moving. But anytime you do a release, you want that release to keep track of the providence that, okay, I was based off of the integration branch, but I want to keep track of the fact that I was also coming off of like the old release branch, the prior version of the release branch. And so you have a parent that points to both, two parents that point to both of those. But you're like, I only want what's on the integration branch, because that's what I have fully tested, and move forward with that. Basically forget all the changes that happened on that old release branch, because those are all obsolete now, because they had already been integrated in on the integration branch. So this gives you those kinds of capabilities, those kinds of choices that you can make for how your workflow is implemented. People often call Git a workflow machine, a workflow toolbox, because you can implement so many different kinds of workflows, and it supports all of them because you're just dealing with pointers, you're moving pointers around, and pointers are really powerful. So Git merge B1, just a slightly different way of looking at it. Our current head is on branch 2, and as I said, this is just a different way of visualizing the same thing. But we'll see why I made this little shift here when we take a look at rebase. So all a rebase is it's a series of cherry picks that are computed and applied to a new base. So the process for rebase is, it's got four steps. However, they're much simpler than the steps involved with the merge. You find all of the commits in the current branch until it gets to a common ancestor. Update head to the new base. This is where you will often see the detached head situation. And then for every patch in that change set, we'll take a look at exactly what this looks like in just a moment. You apply the cherry pick to the head and move the head to the newly created commit, and then you update the branch's head to repoint to the head of the branch. Those are 4 extremely simple steps, but it makes less sense here. It'll make a lot more sense when we take a look at the graph. So what happens is, again, if our head is pointing to branch 2 and we go git rebase branch 1, it's going to go, okay, what's my common ancestor? Oh, it's this A commit. So my change set is B and C. So it's going to create a recipe, and it calls it that, a recipe of, okay, I need the cherry pick of B to A, and I need the cherry pick then of C to B. So here I represented it as, okay, I'm going to apply that patch of B to A as B prime, and that patch of C to B as C prime. And what it's doing is it's basically picking these commits up and reapplying them on a new base of branch 1, which is why it's called a rebase. Now, what's really nice about this is that it means that instead of having a situation like this where you've got multiple parents that you have to follow, you have exactly one parent to follow. In other words, instead of branching around all over the place, you have a linear history. Linear histories are much, much, much easier to understand and follow, reason about, compute on, etc., etc., etc. Linear is awesome. Graphs are useful, but much more complicated. But, and this is one of the reasons why rebase is so confused out there, is if, for example, you had a branch 3 that somebody else was working on, and it also pointed to C, and you do this, and this is like your integration branch, the main yellow is your integration branch. What you have effectively done is kind of move things out from underneath them. And so that can cause confusion if you don't know what just happened. If you know what happened, it's really, really easy to recover from, because, again, all it's doing is it's applying a series of cherry picks. And if you're, especially if you're keeping up with things, if you're doing continuous integration, okay, so you have to reapply 2 or 3 cherry picks, and you might have some some merge conflicts going on with that, but they're individual merge conflicts where, again, if you understand what's going on and how it's applying either that end merge where it's doing the 3-way merges when you do a merge commit, or if you understand what's going on when it's doing the merge with a cherry pick, basically you get the option of picking which route you want to take for how you do those merges. It gives you a whole lot of power, a whole lot of flexibility, and a whole lot of capability to make life much easier, simpler, more predictable on yourself, especially when you're dealing with nasty merge conflicts that can happen, especially if people are making like big, architectural style changes to things. This allows you to be much more surgical in how you apply that, as well as just having a linear history. So if you ever want to know, like, okay, when exactly did this show up on my integration branch or in my release branch? This is a linear history. It shows you exactly when it showed up, as opposed to having to follow all those pointers around, which can get very confusing, whether you're using a bisect or a log or a diff on exactly how that moves around in there. Linear is not confusing. Following all those various routes is. However, again, because it is effectively rewriting history, anything that you have pushed, you need to be careful about how that happens. And there's a lot of workflows around how to manage that so it's entirely safe. But you have to be aware that that kind of thing can happen. So that's the primary difference between rebases and merges. Another thing that rebase lets you do is, because it builds that recipe, is you can step into the recipe and rewrite the recipe. So that change set. So with that, we can do an interactive rebase. So we add the -i to it. And what that does is it'll bring up, okay, here's all the commits that are part of this change set. And typically it'll say pick, 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 followed by the hash of the commit, followed by the commit message for the commit. And then you can do whatever it is that you like, because you have access to rewriting the change set that it's going to be using. Typically, what you're doing with that is you can do things like squash those commits. So you can say, okay, these last 5 commits, I want to squash them together into a single commit, because logically, they're basically 5 different things, five times that I did a commit, but it's logically one thing. And so you can squash those together. You can reorder them. You can edit the commit message. You can do any of those kinds of things. You have full control on how it's going to apply that new change set. One thing that I do, as I mentioned before, where I'm making a change commit, make a change commit, make a change commit. Every time that I see that my change is good because my test pass, because I'm TDD, I know that everything is good because my test pass. again, what that means is I've just created a whole bunch of commits by the time I've reached a good stopping point for the work that I've worked on. And so I've actually have a couple of aliases that I've created for Git, where it's like git fix up, git fix up, git fix up every time. And then when I'm finished making those changes, I do a git -q do squash, and it just automatically squashes all those commits together, and I'm ready, good to go. Makes things really fast, really easy, and I have all the safety that my revision control system can possibly provide to me. So, in conclusion, simplicity brings power. Trivial data structures and a few simple architectural principles provide an extremely rich, fast, flexible, and easily customizable tool. And here in the references are, some things. The title of the presentation, Git Made Simple, is in reference to Rich Hickey's classic talk on Simple Made Easy. Rich Hickey is the creator of Clojure. And where he talks about the difference between simple and easy. Just to break it down really quick here, because it's really apropos to this discussion, is that simple means not complex, very, very simple rules, and not complected. He talks about that, where things are tied together and interwoven. That's as opposed to easy, where, for example, for me, the English language is easy because that's what I grew up on. And so it's an easy language. However, anybody that knows English as a second language knows that English is not a simple language. It has all kinds of crazy rules around it that you learn as a kid growing up with English, but anybody that has to learn it finds out just how complicated English is. Another famous example from computers would be like Unix is simple but not easy, whereas Windows might be easy because that's what everybody's used, but it's not simple. And whereas for a lot of revision control systems and other things that people have worked with, something like Subversion or VSS and the like might be easy because that's what they know, but it's not simple. Git is very simple, but there's lots of things that you can do with it. And so actually learning it and understanding what it does is not necessarily easy. So that's what that reference is about.